Okay, so now with linear regression, we're in module 6, and so we're at the midpoint really of the things that we're going to capture as our statistics knowledge base. So we're in prediction, and so this is our way of using correlation. Correlation is really the backbone of regression, but now instead of just looking at a relationship, we're actually able to talk about the slope and the strength, the direction, and we can predict future outcomes based on the information that we currently have. So what you need to know for this class, the textbook goes really deep into estimating different models and looking at the different regression equations and the different types of regression. Really what I need you to understand at this point is that regression is you predicting a line, and the strength of the line really helps you indicate how accurate your model or the predictability of your model is going to be. So if I have students and I want to know if they're going to pass the RD exam or not, then I want to estimate a model that is very good so that I, as an internship director, can choose those students that are more likely to pass the RD exam. And I don't want a model that's not accurate, because then I'm going to choose the wrong students. So the first thing that you do, as with any statistical test, is you look at assumptions. And something to consider as you're reading through your textbook is that regression has additional assumptions like multicollinearity that correlation and the other testing that we've done prior to this module has not had. So pay particular attention to the assumptions testing required for regression. So when I need to predict something, it's essential for teaching and for nutrition and for medical care and all kinds of different occupations and just things in general where we need to predict. So even statistical models are used in meteorology to predict weather. And so it's essential that we have very good and very stable models. And so, I want to know what students are going to pass the RD exam. And so this is one of the most, the easiest example for me to use, is that, when you're applying to an internship, a dietetic internship, you have to put in your science GPA, your DPD GPA, your overall GPA, your GRE scores. You have to have recommendation letters. You have to have a personal statement, all of these different pieces. And so what we did was look at, okay, everybody that has ever passed the RD exam, let's go back and get their GRE scores, their science GPA, their DPD GPA, and their overall GPA, and see if we can predict from those which one is the best predictor of passing the RD exam. And we did that, and what we found is it's the science GPA. And so that's why there's so much emphasis placed on the science GPA, because it's what we know is going to best predict success on the RD exam. And so they do that for medical school. That's why there's MCATs and dental school and law school. So all of those professional programs have this idea that if they have people that can make a certain score on their entrance exam, then they're more likely to succeed as that in that profession. So regression analysis is the most common statistical procedure for prediction. And so what we want to do, the whole purpose of it, is to identify which factors can explain our outcome. So, what can we figure out that's going to explain what happens later on down the road? Sometimes we focus on prediction because we don't really know or have even a thought or hypothesis, and so that is exploratory. And then sometimes we use it to confirm a theory. So maybe I know that smoking leads to lung cancer, so I'm going to put in that in an equation and confirm my theory and say, this is one of the factors, like smoking, obesity, metabolic syndrome, any of those things I can put into my equation to predict heart disease or cancer, those types of diseases. And so it's used in epidemiology. So with predictions, this regression is predictive statistics, and so it's based on probability theory, which is likelihood, and not decision theory. So a prediction is where you have an independent variable that causes variation in the outcome, or the dependent variable. And so be very, very, very careful not to get confused by the terms independent and dependent variables, because in regression, you are not looking at intervention research. There is no like pre-test, intervention, post-test. Regression analysis is really kind of in a way cross-sectional. It's not intervention research at all, but you still have an independent variable that affects the outcome variable. So the goal of it is to determine what degree the independent variable actually can predict the outcome. So this is the same as what you saw with correlation, where you have -1, which is a perfect negative or a perfect inverse relationship. +1 is a perfect positive relationship, and 0 means that you have no relationship at all. So these are where some of those videos are linked out that are very helpful to talk a little bit more about linear regression. So simple linear regression is the most simple form of regression, and it's where you have a dependent variable and an independent variable. So it's a one-to-one. I don't have multiple things going on. I'm just saying, okay, this is a simple relationship. I'm going to see if I can predict one thing from another. And when I have a simple linear regression, I get a regression formula that looks like y equals bx plus a, because that's the formula for a line. When we talk about multiple linear regression, we'll add more into that equation. But y is going to be my outcome. X is my independent variable or my predictor variable, and then B is the slope of the line or the increase in value, the change score, however you want to describe it. And then A is the y-intercept, which tells me where the regression line intersects the y-axis. So if I have y equals bx plus a, that's going to give me the line of best fit. And remember that it's not a perfect fit, but it's the best fit, because there really isn't any regression equation that you're going to find that has a perfect fit. So this is an example of a linear relationship, and so this line is created to show you the line of best fit. So it's the one that comes closest to the biggest number of data points. And so I want to illustrate for a second about lines that, so if I have a line that shares the same intercept, I'm going to come out from this y-axis. So maybe I'm sharing the same intercept, but I don't have the same slope, or I have a different gradient. Now, if I was to, let me get rid of these real quick. Okay, so now I want lines that are going to be the same gradient or the same slope, but different intercepts. That's supposed to be a straight line. And then this. And so now they're kind of parallel to each other because they have the same slope, but they don't intersect the y-axis at the same place. And so the slope would be the same, but the predicting outcome is not. So my dependent variable is going to be continuous. My predictor variable can be any kind of numeric value. And then the goal is to have an equation that I could plug numbers in and predict future participants' values. So if I'm a high school teacher, I want to plug in, you know, their math GPA, their science GPA, their English or language arts GPA, and maybe their ACT, Aspire, and then see which ones are going to succeed in college or who gets the biggest scholarship, things like that. So I can do that 1 year, and then I would hope that every year after that, I would just have to plug in the numbers and the equation would remain accurate. So again, we're looking at the line of best fit, not the line of perfect fit. And I use the method of least squares to describe my line and to create my equation. And when I think about the difference between simple linear and multiple linear regression, the difference really is that a simple linear regression shares or has one independent variable and one dependent variable. Multiple regression uses multiple combined influences, which really occur more often in nature, to predict one outcome. So now I could do, if I thought that smoking and sedentary lifestyle and a high-fat diet all led to heart disease, then I could do 3 separate regression equations. I could say, okay, smoking to heart disease, bad diet to heart disease, sedentary activity to heart disease. But what that's going to do is inflate my alpha, or my rate of error. And so I'm more likely to get a false positive or not reject my hypothesis if I go on and do those 3 separate tests. So what I want to do is a multiple linear regression where I can put all 3 variables in the equation at one time and then spit out an equation that is going to tell me about my outcome. So linear regression is a way to estimate the value of a dependent variable based on an independent variable. Multiple linear regression is an extension of simple linear, and it gives you multiple independent variables to predict your outcome. So at the end of the day, the thing that you have to remember about simple linear regression is this y equals bx plus a, because that is really the key of the line. That's the equation for a line. So your y is, or I'm sorry, your a is your intercept on the y-axis, and then you have your slope to give you the amount of change. And so the outcome is your regression coefficient r. When r is squared, it gives you the variance in the data that can be explained by your equation. And this y equals bx plus a is your equation. So when you get r squared, it tells you how much variance that your equation can explain. So think back to your correlation, and you have your Pearson's correlation coefficient, which was r. So r squared is just your Pearson's correlation coefficient squared. And what it is your sum of squares for your model divided by the sum of squares for the total. So what you want to do with linear regression, simple linear regression, is test for your assumptions and look at your scatter plots. Then I'm going to use the variables of income and education to run a simple linear regression analysis. So what I want to know is if education level can predict my income. So which one is going to be independent and which one is going to be dependent. If I want my income to be the outcome of my education level. So I'm going to go to Analyze, Regression, and I'm going to choose my linear regression. And then I have my variable list. So I want to identify my household income, and I want to identify my school level completed, because that's my education. So I want to know my outcome variable is my income. My outcome variable is my household income. So that is my dependent variable. My predictor variable is my school level. So if I was writing a research question, I would say, to what degree does education level completed predict future household income? So I want to go to my statistics block, and I want to choose estimates, model fit, and descriptives. And then I click continue, and then I click OK. And it gives me my result. So the first thing that you have to notice is that income and school level were both categorical variables. There might have been 14 categories, but they were both categorical variables. So this was a terrible example to use, but I wanted to make the point that you can use categorical variables in regression, but you need to have more than 5 categories, because you can kind of consider it, if it has more than 5 categories, as continuous data. So both of these had way more than 5 categories, so you could consider it continuous, but it's still really hard to interpret, because a mean of 7.34 when I'm talking about income is pretty meaningless. Like if 0 was less than $5,000 and 14 was $150,000 or more, a 7 doesn't really tell me anything. I can't say that if the mean is 7, then the majority of the sample makes between $50,000 and $60,000. That's just not, I can't do that. So it's kind of a useless descriptive statistic. What I would prefer to see would be, first of all, that you don't have categorical data, that you're using it, that you just use continuous data. But if you have to use categorical data and consider it as continuous, then you would need to show me the N, or the frequency, and the percentage. So 8 people said they made $0 to $5,000. 10 people said they made $5,001 to $10,000, and so on. So then I go to my correlations, and this is telling me that I have significance at, let's see, income and school is significant, and that's my only correlation, because I only was looking at 2 variables, 1 to 1. This N is telling me I had 269 people that did both that completed information for both variables, and then my coefficient is the 0.212. So it tells me I do have a significant but weak relationship. So with my regression analysis, I keep going, and I want to look at my ANOVA. So this is my ANOVA table. And my ANOVA table is called an F test. And so an F test, I can't make an F. There we go. An F test is an omnibus test. It means that it tests the overall model. And so if this is not significant, like if this is greater than 0.05, then the entire model is not significant and I just move on because I can't talk about it. But this significance level is 0.000, so it is significant. So then I can go down to my coefficients and say, okay, my household income in the last 12 months is a significant predictor of my education level. So this is a blown up example of the chart that we just saw, or the table that we just saw here. So when I'm looking at this, my constant is 6.017. So that means that if my household income was 0, then I'm going to have an education level of 6. It's just super hard to conceptualize because we use categorical variables. But even if I reported no income at all, I would have at least had a 6 on my education level. And then I go to my beta, which is my slope right here, and it tells me that for every 1 unit increase in my education level, I'm going to increase my income by 0.057 units. So again, this is really hard to conceptualize because it was categorical variables. But if this was dollars, for example, and this was grade, then you would say at $0 income, people at least had a 6th grade education. And then for every unit increase in education level, then you're going to have a decrease. You're going to, so for every unit increase in education level, then I'm going to increase by, let's say, $1 or $1,000, however that. But remember that the way that we talk about, or the way that we interpret regression, is very, very important. So for every 1 unit increase, there's a blank increase in, or if it's a negative relationship, then it's a decrease. But only if, and only if, your ANOVA is significant. And so when in your write-up, that's part of what you have to say in your conclusions, is you have to interpret it in terms of, for every 1 unit increase in X, there will be a Y increase in the other variable. So then you need to work on plotting your regression line, because it's important to actually see the line of best fit. And so this is a terrible example again, because we use categorical variables and pretended they're continuous, and it gives us this terribly ugly chart. But what we see over here is that we fit the line to it, and our R-square is 0.045. Now, if I use continuous data, I get a chart that makes a little bit more sense, like weight and body mass index. Now, we know that those are highly correlated because weight is a function of body mass index. You have to use weight to calculate BMI. So my R-square here is 0.829. So that means that my equation is explaining 83% of what's going on. So there's only 17% of stuff that I don't have a clue about. On this example, I'm only explaining 4.5%. So that means there's 96.5% of stuff that's going on, and I don't have a clue about it. So it's important that we look at that R-square. So just to kind of one more time wrap it up, when you have a straight line, you're going to have this equation, and your little b, is your regression coefficient for the predictor. It's the slope of the regression line. Your B0 is your intercept, and so that's the value of y when x equals 0. So if I'm thinking about that and I'm looking at my chart, so this right here is my B. This is my B1. This is my B0. So this is my y-intercept. This the constant is, because it doesn't change. It's the intercept. The gradient helps us explain. Well, the slope and the gradient are the same thing. So with our intercept and gradient, I can have a positive or a negative gradient or slope. And then my intercept is always going to be a constant that where it hits the y-axis. So now with my method of least squares, what I'm looking at is I have my line of best fit, and then I'm looking at the actual data points and how far away they are from a data point that would actually be on the line of best fit. And that helps give me a trend. But what I count in between are the differences, the residuals. So I can have positive differences and I can have negative differences. And this is in your textbook, and what it's showing you is the amount of album sales and the budget. So as the number of album sales increases, the amount of the advertising budget increased. So the regression line is only a model. It's not a fact. It's just a model. And the model might not reflect reality. Just like we talked about, correlation is not causation, and you can have completely spurious correlations that don't make any sense at all. You can still have a regression model that doesn't exactly reflect reality. So now, if we look at our sum of squares, this is part of our model. And so again, these are data points, and what we are looking for is the residual difference between the actual data point and the line of best fit, or the mean. So our sum of squares for total variability is the variability between the score and the mean. Our sum of squares for the residual or the error validity is the variability between the regression model and the actual data. And then the model variability, or the SSM, is the difference in the variability between the model and the mean. And so like here, this is going to be our total variability. This is going to be the variability between our scores and the mean. Whereas when we were looking at this one, this is more of what you're looking at with your sum of squares of the residuals, or the error. So your ANOVA, let's circle back to the ANOVA. The ANOVA is the omnibus test. It means that it's the big picture, it's the umbrella, and it's the stopgap. If you don't have a significant ANOVA, stop, turn around, and start over, because if you don't have a significant ANOVA, then you can't continue on because it doesn't mean anything. So your F, your value, the ANOVA value, is an F statistic. And that's the mean square of the model divided by the mean squares of the residuals. So this is the example, one of the examples from your textbook. And so you're looking at predicting album sales from advertising. So you have your outcome variable is sales, and your predictor variable is the money spent promoting the album. So what you get is you have to figure out which one is your independent variable and which one is your dependent variable. So your dependent variable is the sales, because you want to know how much the budget impacted the outcome. So how much the budget impacted the sales. So when I get my summary, this is just telling me what my model was. My R is 0.578, my R square is 0.335, which tells me that I can explain 33.5 of the variance. So 66% of it cannot be explained by this model. And then I'm going to go over to my ANOVA table, and I see that it is significant. So I'm going to say, yay, I can keep going. But what I need to look at is the different pieces of my ANOVA table. So I know that the sum of squares for my model is going to be this huge number, and my sum of squares for my residuals is the 862,264, and then my sum of squares total is even bigger. So my mean squares and my mean squares residuals are what can be calculated from the sums. So my F value is 99.59, and it is significant. So I can conclude that the regression model is a significantly better predictor of album sales than if you use just the mean value. So your null hypothesis is using your mean value, and you want to reject that null hypothesis. So the problem is that the ANOVA doesn't tell us about the individual contribution of variables. So this was easy because I only had one variable to contribute, which was my budget. And so I look at my unstandardized coefficients and my standardized coefficients and my significance. So the significance here, I know that I can look at this because my ANOVA was significant. So it tells me my advertising budget is significant. So if I have a $0 advertising budget, then I'm still going to be able to sell 134,140 albums. So now for every 1 unit increase in my budget, my advertising budget, it could be $1,000, $100,000, whatever the unit is. If my advertising budget is increased by 1 unit, then I'm going to sell 96 extra albums. So 1,000 was what the unit was. So if I increase my advertising by $1,000 or 1,000 pounds, then the model is going to say that I'm going to get 96 more sales. So that's a pretty bad investment, return on investment, if I'm inputting $1,000 and only getting 96 sales out of it. And this is another one of the really good videos to help you understand a little bit more about interpreting that output. Okay, so for multiple regression, again, this is a regression equation. We're in the middle between a relationship and being able to establish causality. So we still can't establish causality because we're just talking about relationships. So I want you to be able to use multiple regression and simple linear and know when to do that. You need to be able to test assumptions and recognize what assumptions you need to test and how to actually do the multiple regression in IBM SPSS. So your linear regression is a model where you predict one variable from the other. So this is a review of what we were just talking about. Your multiple regression is a natural extension because we know that in the environment or in nature, there's not just one thing that causes an outcome. There's multiple things that work together. And these videos are all very good to talk about the basics of multiple regression. So again, prediction is essential, but we can't just predict one for one. We have to think about the bigger picture and all of the other aspects that go into an equation to be able to accurately predict an outcome. So again, do not get the independent and the dependent variables confused with intervention research. Our independent variable is what is helping us to talk about our outcome. So we can look at linear regression, which we already did. Right now, we're going to talk about multiple regression, odds ratio, and logistic regression. Odds ratio is something you get when you do a logistic regression. There's entire semester-long classes just on logistic regression. So we're not going to do that. We're going to spend just a minute talking about what it is, but we're not actually going to conduct one. So multiple regression has a lot of very complex calculations. And that's why we use a software package, because if we think about this equation where we have this y equals a plus bx. So the bx1 is one variable, bx2 is another variable, bxi. So it could be n, nth to the nth b. And so every time you have another variable that's put into the equation, then you have to change the weights of every other one. And so it could get super complex very quickly. So sometimes variables are related in a predictable way, and sometimes they're not. And so if you're doing it by hand, it could be very cumbersome. And again, the difference between simple linear and multiple regression is that if you do multiple simple linear regressions, then you're going to inflate your chance of error. So it's more accurate to do one multiple regression. And so your beta values for your predictor are tested for significance. Your R-squared is computed to tell you how much variance you can explain. And then with a multiple regression, all predictors are tested simultaneously. Each beta value is adjusted for every other predictor in the model. And that's another reason why it can get so complicated. So your assumptions for multiple linear regression, the first is that you have dependent and independent variables measured without error, that you can treat your variables as interval. So like we talked about, they ideally should be continuous variables. But if you have more than about 5 categorical, you can treat them as interval. It's just really, really hard to explain or to interpret. You have to make sure that your residuals are not correlated, your scores need to be homoscedastic, and you need to have equal variance at each value of X, so a homogeneous variance. And you also will use a number of different procedures to ensure that your assumptions aren't violated. So you'll do your normal assumption testing and also look for multicollinearity. So generalization is something that's really important in regression, because you want to be able to say, more than I can just predict who's going to pass the RD exam for students that go to UCA. I want to be able to say, I can predict the pass rate on the RD exam for students in the nation. So you want to make sure that you're able to meet your assumptions so that you can better generalize your results. So the things that are pretty straightforward that you've done all along have been checking on the variable type, looking for non-zero variance, looking for linearity, and then testing for independence. What's new is that you need to test for multicollinearity and homoscedasticity. The independence of errors and the normally distributed errors kind of follow along with the multicollinearity. So as long as you're testing for multicollinearity, you should be fine. What multicollinearity is if predictors are highly correlated. So you look at your collinearity diagnostics when you run your regression test in SPSS. So now a logistic regression is where you have an outcome variable that's categorical. So either you have a disease or you don't. So either you're male or you're female. That's the terrible example. Either you're male or you're not. Either you're female or you're not. Either you're pregnant or you're not. Those are examples of categorical outcomes. And so what you're doing is calculating the odds of actually having that outcome. And so this is used a lot in epidemiology and biostatistics because it's very, very important for us to be able to say if you've smoked, your odds of getting cancer are 1 in 10 or 2 in 10, whatever. Now, this is way beyond the scope of the class. You would imagine that if you have a categorical variable that's either you have it or you don't, then it's going to be super easy to interpret. But in reality, it's even harder to interpret because you have to look at the odds ratio. And so the odd ratio is looking at a particular exposure and the risk for your outcome. So if you have an OR of 1, then you're not going to get the predictor doesn't have any effect on if you're going to get the outcome or not. If you have an odds ratio of greater than 1, then if you're exposed like to sunlight and your outcome is skin cancer, then you're going to have a higher chance, and you've been exposed to sunlight, then you're going to have a higher chance of getting that skin cancer. So odds ratios are really complex to interpret. With regression, so going back to our standard multiple regression, you can do hierarchical, stepwise, or forced entry. Hierarchical is where the experimenter decides which order you're going to enter the variables into the model. And so this is if you have a hypothetical reason why you're going to do certain things, like you know that one thing comes before another, and that comes before the third thing, which then leads to the outcome, then you would put it in that order and look at the model. Stepwise predictors are when you have semi-partial correlations, and that stepwise is usually done by the computer, and because it's very intense mathematical equations. And then forced entry is what we're using because that's where all your predictors are entered simultaneously. It's where you really don't have a hypothesis about what's happening, you just want to make the best model. So with hierarchical regression, experimenter makes the decisions. You need to know what hierarchical regression is and that you have a hypothetical reason for doing it, but we're not actually going to conduct these tests. And then with stepwise, again, this is a very highly mathematical procedure, and so your computer is the one that uses an algorithm to select the variables. Forced entry is where we're focusing all of our attention, and this is putting in all of your independent variables at once, simultaneously into the model. So semi-partial correlation. A partial correlation is where you see the relationship between two variables, and it controls for the effect that a third could have on both of them. Semi-partial is where the relationship between two variables, and you control for the effect that a third variable has only on one of the others. So with semi-partial correlation in regression, you're measuring the relationship between a predictor and the outcome, and you're controlling for the relationship that the predictor has on any other variables that are already in the model. And so what you look for is a unique contribution of that certain predictor to your outcome. So with multiple regression, this video, the first video, doesn't use SPSS, but it gives you a lot of really good information about the background on regression. The second one I didn't think was as useful of a video, but it does use SPSS, so it might help you as you go through your steps. So the example here is we're going to use one dependent variable and 2 independent variables for our multiple regression because we want to make it more than a simple linear. So if I think about the ones that are continuous and the things that I suspect or I hypothesize might have an effect on a dependent variable, I think maybe I want to look at BMI change and then total steps walked and fiber intake, because those are all continuous. So the first thing I have to do is some pre-testing or some assumption testing. So I look at the histograms, I look for homoscedasticity, make my decisions about if those variables are normal or not. I'm going to assume, even if they aren't normal, that my teacher told me to do them, and so I'm going to use them anyway. I'm going to go to Analyze, choose Regression, and then I'm going to choose Linear. So then I'm going to move my dependent and my independent variables over, and I'm going to click on Statistics, and I want to select the estimates, the model fit, descriptives, and now I'm adding in my correlations. So in this example, the first thing that I look at when I get my output is my significance. So I get 0.094. So that means that it's greater than 0.05. So I might as well just throw this out because I can't talk about it any further because the overall model is not significant. So in my results section, I would say the overall model is not significant, parentheses, p equals 0.094, close parentheses, period. If it was significant, so pretend this is 0.04, then the next thing I'm going to do is look at my coefficients table and see which one of my coefficients was the one, or maybe it's both, that were significant that drove the ANOVA to be significant. But I can see from this table that neither one of them were significant, which explains why my overall test was not. And so my F test, again, is my ANOVA. It's my omnibus test, and it tells me about the variance of the sum of squares for the model and the sum of squares for the residuals. And so it tells me if my regression model is better than just using the mean. So if I have, let's see. So if I have my equation here, and I want to, so pretend this is my mean, and then I have all my data points spread out everywhere, all around. And if my value for my sum of squares for my model and my sum of squares for my residual is perfect, then that tells me that it's distributed around the mean. But if I have this line that comes through and I hit most of my data points with this line of best fit, then I would expect that the line of best fit explains more variance than the mean. And so when I have something like an ANOVA, it's telling me, oops, there we go. It's telling me that my model is significantly better than just using the mean. So my R is my correlation, is my Pearson's correlation coefficient. My R squared is my Pearson's correlation coefficient squared, and that tells me the variance accounted by the model. And then my adjusted R squared tells me the population estimate, or the shrinkage after, and what it would look like if I was to generalize my values. So my beta values change with the outcome associated to the predictor, and my standardized beta gives the values in standard deviations. So with my beta value, what's really important for me to think about is that, again, when I'm reporting this in the result on the conclusion section, that I have to say for every 1 unit increase in the predictor variable, that there's going to be the dependent variable increasing by the unstandardized beta coefficient. So you fill in the blanks. For every 1 unit increase in predictor variable, for every 1 unit increase in sun exposure, the risk of skin cancer will increase by 0.25. I don't know, I just made that up, but that's how you would phrase that in your conclusions. So our B0 is our intercept, and it's the value when all of our x's are 0. And this is the point where the line crosses the y-axis. So I can have B1, B2, Bn, all the way up to however many variables I put in my regression equation. So what we're going to do is assignment M6. So assignment M6, you're going to have 2 linear regressions and a multiple regression. So you have 3 separate research questions. So what I want you to do is to take all the variables that you're using and write your introduction with paragraphs about each one of those variables to introduce them. And then you're going to have a methods section for, it's going to be one method section, but it has like your linear regression explanation and your multiple regression explanation. You need to talk about each test, how there's the similar, how they're different, why one test is appropriate for one research question and the other test is appropriate for the other research questions. And then in your results section, you're going to again have 2 separate subdivisions where you have a linear regression subdivision and a multiple regression subdivision. So you want to test for assumptions underneath each one because you're using different variables, and for every set of different variables you use, you have to do new assumptions testing. And then your conclusions can summarize the overall findings, but remember you have to interpret it according to like what we talked about with the for every 1 unit increase in X, there will be a such and such increase for Y. So for the first part of your homework, you're going to use total cholesterol and systolic blood pressure at 0 to predict BMI at 0. So this is a simple linear regression. So that means you can only have a 1-to-1 variable. So you do two separate analysis. So like your first research question is going to be, to what extent does total cholesterol at baseline predict BMI at baseline? And then your second research question, to what extent does systolic blood pressure at baseline predict BMI at baseline? And so you have to think about which one is going to be in your dependent box and which one is going to be in your independent box. So this is 2 different analyses that are both simple linear regressions. And then for your second part of your homework, the big picture is that you're going to find out to what degree baseline food frequency can predict household income, sedentary minutes, household food frequency, household income, and sedentary minutes can predict baseline BMI. So there is currently no variable in your data set called food frequency. So you have to make that variable. Like FFQ-0 is what you're going to call it. And what you do is add calcium, dairy, fiber, fruits, and veggies, and then subtract sugar. But remember your order of operations, that you can't just subtract sugar from all of that, because if you did it like this that I have on here, then you would just be subtracting sugar from fruits and veggies. You need to subtract sugar from calcium plus dairy plus fiber plus fruits and veggies. So write your research questions. Create your new variable. This is a video on how to do your new variable. Test your assumptions on your new variable and the other 3 variables, and then write up your analysis. So you're going to have 2 simple linears and 1 multiple linear. And this is just an example of some results, but remember that you would have to put in your z-scores for all of your skewness and kurtosis, and you also have to put in your significance from Levine's test. And then in your actual write-up, this is a good example of how to write the model, and then looking for your slopes and your standardized slopes. Okay, so let's go to SPSS. And let me find that data file. Okay, so we see that our data file M6.2, and so I've already calculated this and this one, but if you go to transform, compute variable, and then you're going to find the ones that you need to add up together. So you find calcium plus dairy plus fiber plus fruits and vegetables. And remember, I can't just subtract sugar. I'm going to go on and add it in, but I'm going to put my parentheses around it to indicate that I need to add these up before I subtract. And then my target variable, I'm just going to type in FFQ_0 and then hit OK, and it creates my variable. So the next thing is, if I do a regression, I'm going to go to regression, linear, and then I want to predict, let's see, I want to use money spent on eating out. So I want to see if I can predict total cholesterol at 2 years based on money spent on eating out. So I have to go to my statistics, estimates, model fit, descriptives. And so this is going to be a simple linear equation, a simple linear regression equation, because it's just a one-to-one relationship. If I spent, if I said, money, let's see, total cholesterol, systolic blood pressure, let's say age at baseline. Well, now I'm going to need my part and my partial correlations to see if there are relationships there. So then I hit, well, if I say enter, that's going to be the forced entry method. These are the other types of methods that we can use. And so like if I chose stepwise, I would put my variables in there and then I'd go to my next block and put in new variables. But that's not the way that we're doing it. We're going for enter. So then I would hit OK. And my regression comes up. So remember, I just went straight through. I didn't do any assumptions or descriptive statistics. I just went straight into my linear regression, which is not the way that you should do it, but I wanted to show you an example. So I know that my means are here, and these are all continuous variables, so I'm good to go. And I see that I do not have relationships, correlations. So I would not expect my ANOVA to be significant if I don't have any relationships at all, and it's not. So now my age in years is significant, but my money spent on eating out is not there as part of my partial or part correlation, semi-partial correlation. So if I look at my significance values over here and my coefficients, they're terrible. And so that's why this ANOVA is also not significant. So if you have any questions or anything, make sure to reach out and let me know. And remember that this is due, it's a 2-week module.